simplicity of carbonyls. Aldehydes were most electrophilic, followed by ketones as their second and most. Then esters is our third most electrophilic, amides is our fourth, and then our least electrophilic was carboxylates. So we just made our least electrophilic carbonyl derivative because this had to grab this proton. And furthermore, this equilibrium is going to be really favored because the pKa of this carboxylic acid is 4. The pKa of this RO minus is 16. So by 12 orders of magnitude, this step's going to be favored to give us the RO minus. And so this explains why we get primarily this product, why the equilibrium favors this. Because even though in the step where we kick out the OR minus, it's not going to be that favored because pKa argument, we're talking about kicking off a group with the pKa of 16 versus kicking off a group with the pKa of 16. So there's going to be no preference for which one of these kicks off. But when we kick off the OR, it gives us now an acidic thing that the basic addition is going to be protonate and funneling this out to the product. And so one thing we can think of this is when we deprotonate the carboxylic acid, this is going to be so much more unreactive because this O minus is donating so much lepton density into the pi star orbital that it's no longer as electrophilic. We can almost look at this as just falling out of equilibrium. From Le Chatelier's, it's just falling out of equilibrium and causing the rest of this equilibrium to catch up and eventually funnel to that. So under basic conditions, we get out the carboxylate because of these thermodynamic implications. And of course, when you're done, you add some H+, and you have your carboxylic acid. So, an overview of really the important stuff for the carboxylic acid, for ester chemistry. You make esters, acidic conditions, and alcohol. Or you can make the acid chlorine and add an ester into it, and but that's reviewed from a few days ago. But the big thing new from today is you can make esters taking your carboxylic acid and acidic conditions and methanol or whatever alcohol you want to add in. You did this in the lab, so it's reasonable to do. While you can use acidic conditions to deprotect it, the easiest way to deprotect an ester or to take an ester to a carboxylic acid is through these basic conditions. When we take sodium hydroxide, or some hydroxide, it doesn't have to be sodium, but sodium hydroxide is a good one, and run it in some kind of mixture of organic and water solvent so that our ester can actually dissolve in. And then it's a matter of just sodium hydroxide, which is a strong base and a strong nucleophile, adding into the ester, giving us a stepicular intermediate, which can kick off either OR or OH. If it kicks off OH again, it's going to go back to the starting material. If it kicks off OR, it gives us a carboxylic acid, which is quickly deprotonated. And this quick deprotonation is what drives the equilibrium, because this is just going to fall out of equilibrium as the carboxylic, as a carboxylate. So this is almost similar to when we were talking about dianyl chloride and giving off SO2 as a gas, which bubbles away and that drives the equilibrium to the product. This doesn't bubble away, but it's just so unreactive, it might as well have bubbled away. And so this being very stable and falling out of equilibrium under these conditions really drives the reaction to the carboxylic, the carboxylate, which then we can protonate with a strong acid to get our carboxylic acid. Yay. So now what? The big thing in this chapter now is amides. Yes.
So, you know how we have 4-to-1 ethanol.
Yeah.
So if carboxylic acid wasn't so stable, then that would this thing would not work. This gets.
Yeah. So for instance, if you had just sodium hydroxide and methanol and there's no water around, so it couldn't actually. Well, and what's your question one more time?
If carboxylic acid wasn't so stable.
Well, it's not that the carboxylic acid is stable.
I mean,
it's that the carboxylate is so stable. So yes, you're right. So if in theory the carboxylate weren't stable, it wouldn't work. But because the carboxylate is so stable, you can run this in methanol, which you would think would make this completely anti-Le Chatelier's, because usually you use Le Chatelier's by using one of your things you want to add in as a solvent to drive it towards the product. And in this case, this does, you think methanol would want it to drive it towards the methyl ester. But because when we form this, it quickly breaks down to this, eventually everything's going to funnel to this, which we can think of as a thermodynamic sink. So this is just chemistry that's fairly, can't make up its mind, it keeps flip-flopping, but the second it forms this quickly forms this, and that's stable. And just follows out of equilibrium. And then by Le Chatelier's, since this is now stable and following out of equilibrium, so by forming this, we're removing this from this equilibrium. Because we're removing this from this equilibrium quickly, this equilibrium is going to start shifting towards this. And shifting towards this, and once we form this, this is going to depronate this to give us the carboxylate. Yeah?
Is there anything you can use besides methanol?
Oh, for your solvent? Yeah, you can use THF, DMF. The big thing is you want something that's water miscible. I learned this the hard way as a graduate student. When I just couldn't get these methanol conditions past my head, I'm like, oh, that's so anti-Le Chatelier. That I was stubborn, and I wouldn't use methanol. I'm like, I'm going to use THF or ether. The problem is THF isn't as miscible with water as methanol is. And so what I would get is my reaction would be bifasic. I got my organic layer on top of my water layer in back. My reactions, which should take 20 minutes, would take 6 weeks or 6 days. You'd set them up on a Tuesday, and then on Monday the reaction would be complete. And then finally, out of pure desperation, I gave in to pressure from my friends saying, just use methanol. And so I switched from THF to methanol, and the reaction was done in 20 minutes. Because solubility is important in a reaction too. If your chemicals aren't soluble, they can't react. So methanol is a good one. You can use THF, but be aware. What do you guys use in the lab? What? That doesn't really matter, but I was just curious. Alright, so now what? Pipeline. So that brings us to amides, and I'll use amides the last few minutes today. And I would argue amides are the most important functional group in this class, at least biologically. Why are amides? Definitely this chapter, they're the most important carbonyl biologically in this chapter. Why are amides so important? They build up proteins. They also are the basis of other polymers. But importantly, amides are the building blocks of proteins. So every protein is just repeating, it's just a repeat of an amide bond over an amide bond. So I believe every 3 bonds in a protein is an amide bond. Why did nature choose amides? Well, with the exception of carboxylates, amides are the most stable carbonyl. By most stable, I mean amides are the least electrophilic. So they're the hardest carbonyl other than the carboxylate to have a nucleophile add into. The reason being is we have this nitrogen with these fairly high energy low pair of electrons, which can resonate into the carbonyl. And this electron density going into the carbonyl carbon, as we've discussed several times in this class, is going to make the carbonyl carbon a lot less reactive, because there's going to be more electron density or a less amount of a partial positive charge at the carbonyl carbon. Yes?
That's supposed to be resonance arrows, right? Positive tension.
You are right. So because of this, amides are very stable, meaning it's very hard to have nucleophiles add into an amide. So what that means is when the protein's made, a protein's not going to just fall apart. The amide bonds are strong enough so that the protein's just not going to fall apart. So this stability of amides is very important because you don't fall apart. However, whereas they are stable, under certain conditions, you can make them unstable, namely acidic conditions with a very strong nucleophile. And so amides are stable, but because they are carbonyls and you can in theory add step into them, you can develop ways to cleave an amide. But they have to be under fairly forcing conditions. So just for an example, we all eat proteins, right? Obviously, if you eat proteins, we metabolize proteins. If we metabolize the proteins, that means enzymes in us. So we have to be able to break down the proteins, i.e. the amide bonds. So under acidic conditions, we have a lot of enzymes like proteases that can actually go in and cleave amide bonds at specific points, and that helps us metabolize them. So nature chose amides because they're very stable. However, they're not too stable. They're the most stable carbonyl other than carboxylates, but under the right conditions, you can make them unstable. So biologically, it's like the Goldilocks syndrome. They're just right. You know, proteins aren't made out of ketones because ketones, you can't cleave a ketone, right? If you had a polymer of just ketones, right? If this was, instead of using an amide bond, we had ketone bonds, we wouldn't be able to break it. So this is the amide bond that we see in a protein. So a protease can break this under right conditions. However, if nature had chosen to make ketones instead of amides, we wouldn't be able to break apart the carbon-carbon bonds. We wouldn't be able to, so proteins would be too stable. Amides, since they are an ester-like thing, we can still break them apart. But that was me getting philosophical for no reason. So, what do we need to know about amides? Well, from the nucleophilic acyl substitution, we know amides. Well, actually, let's do a quick pop quiz, if you will. Of course, no points. So we take an amide, and we take an ester. Oh, sorry, an alcohol. If we stir this in an alcohol, what are we going to get out? No acid, no base, we just throw in an alcohol. Nothing, right? pKa-wise, it's going to favor the amide. CO minus, nothing. Acetate, so carboxylate, nothing will happen. So pretty much, once you form an amide, with the exception of some reactions we'll talk about later, you're stuck at the amide. So using the typical 4 or 5 nucleophilic acyl substitution we talked about earlier in this chapter, the amide is the terminal carbonyl. The amide is the end of the line. That being said, if you wanted to make an amide, it's not that hard. If you wanted to make an amide, you can take an acid chloride, or an anhydride, or an ester. And these would all go to your amide. Enough space. I'm just going to draw it here. So using nucleophilic acyl substitution, amides are pretty easy. But the problem that's really presented in the field, and it's going to be what we're going to talk about Friday, is amides are one of the most common synthetic groups out there. In 2015, scientists synthesized proteins de novo fairly commonly, especially at the Scripps Research Institute down the street. That's where they kind of started doing it back in the day. There are drugs with many, many amides. There are drugs that are peptides. So a peptide is a shorter amino acid chain than a protein. So amides are very important to make. However, all of these methods here aren't really synthetically feasible across a large industrial scale or making several amides. And so there's got to be a better way to make amides. And so on Friday we're going to talk about the better ways to make amides compared to cloud. And then we're going to finish up the chapter talking about things we do with